Okay, yeah, so we're going to get started. I would like to welcome Dr. Noah Bice for his willingness to give this lecture. It's on a very interesting topic that I myself am very excited to hear about, uh, the principles of inverse planning. And yeah, without any ado, Noah, you can jump in.
Sure. Yeah, thank you for inviting me, and thank you for the introduction. Let's see. Let's try and get the screen sharing down. It's the first step. Is this okay? Can everyone see my slides?
Looks good.
Okay, awesome. So as Joe said, my name is Noah Bice. I'm a physics resident at NYU Langone, and uh, today I'm going to be talking about principles of inverse planning. So like basically the inner workings of IMRT and VMAT optimization, and then we'll talk about some other fun like optimization adjacent topics. It's a topic that's near and dear to my heart. I guess I did a lot of work on it during my PhD. So hopefully I can present things in a coherent manner for everybody. So here's sort of an outline of how I want to approach the topic. We'll start with just a little quick motivation for why we want to use computers to help us do treatment planning in the first place. And then we'll talk about what's going on behind the scenes with IMRT and VMAT optimization. And then we'll talk about some other sort of planning adjacent algorithms and specific optimization objectives that can help us to create satisfactory treatment plans. And then finally, we'll just breeze through some topics in treatment planning research just so that everybody's like on the same page and aware of the jargon and sort of what's going on when they hear about these topics. So I have a few disclaimers here. Most of my personal experience is with Variant Eclipse and some in-house optimization software, but I have limited experience with Pinnacle, RayStation, and AccuRay's Precision, but otherwise I have nothing to disclose. So I guess forward planning is the conventional standard for radiation treatment planning, and I'm just going to assume that everybody is somewhat familiar with it. We have either a 2D or 3D model of the patient, and as a physicist or treatment planner, it's our objective to come up with mechanical parameters to deliver a satisfactory radiation treatment plan, whatever that means. So that means manually setting could be, at least for a C-arm Linac, like gantry, collimator, angles, jaw, MLC positions, physical wedges or EDWs, and beam energy, number of MUs. And this is all done manually by the planner. The advantages of some advantages of forward planning as opposed to inverse planning, which we're about to talk about, are that it's fast, it's easy to understand as far as possible failure modes. It is inherently robust because there are implicit margins because of shallow dose gradients. And however, some disadvantages, which are why we want to talk about IMRT and VMAT, are that you're limited in the complexity of the treatment plans that you can create, meaning that you're limited in conformity to the target, uniformity of your dose distribution, and then just general coverage and OAR sparing. And obviously, forward planning is not completely obsolete. There are like many circumstances in which we're still implementing forward planning at NYU and other places, including like brachytherapy, gamma knife, and I guess for us, it's a lot of palliative treatments. So I think a reasonable place to start for talking about computerized treatment planning is with this question of what is an algorithm? So I guess formally stated, an algorithm is just a process or a set of rules to be followed in calculations or other problem-solving procedures. So the idea behind computing algorithms is that we have, or algorithms sort of form the basis for all modern computing. And the idea behind an algorithm is that we're presented with some complex problem. For example, one of my favorite examples is long division. where we have the seemingly insurmountable task of like putting 17 into 123,456. But we have this long division algorithm that tells us we follow the set of rules and we can perform simpler calculations to arrive at the correct answer. And of course, algorithms are implemented in other day-to-day activities like solving a Rubik's cube, and for us in treatment planning. So this is an example of like the steps written out for inverse planning with simulated annealing, but we'll cover that in more detail in a moment. So the question that we're interested in as medical physicists is how can we use algorithms to improve our radiation treatment plans? So if we think about our conventional treatment planning procedure, for example, like a manual field and field, the sort of steps that are essential in creating a plan are to first define treatment objectives, like what is the prescription dose and coverage objectives, which OARs are we trying to spare, are there dose volume limitations that we're trying to meet. Second, we want to set treatment parameters, based on our best judgment, which could be beam energy, or as all the things that we mentioned earlier, if we're culminating with an MLC, using MLC, which MLC positions to use, how many subfields we want to use if it's a field and field. We calculate dose in a model of the patient, evaluate the plan according to our treatment objectives, and then if we're unhappy, with how the plan looks, we continue to iterate, right? We go back and adjust parameters and calculate dose and continue evaluating. So our problem being human is that we're limited by the amount of time that we can spend doing this process, right? We have like clinical workflows that we have to keep up with, and we're limited in the complexity of the treatment plans that we can fathom, right? When we start to consider, if I wanted to do like a field and field for 5 different beam angles for like an esophagus patient or something, there's at some point, my understanding of how I'm adjusting MLC leaf positions in this particular subfield, how that affects our treatment objectives becomes computationally intractable. So taking a step back, just like along the progression of the development of treatment technologies and radiotherapy, we've gone from 2D patient models to 3D conformal radiotherapy, and then today we're going to talk about intensity modulated radiotherapy, or IMRT, and volumetric modulated arc therapy, or VMAT. So IMRT was introduced in the 1990s by some great physicists, and with the idea that you have an increased capacity for complexity beyond what we're able to achieve with forward planning. So IMRT, at least in our clinic, is typically like somewhere between 5 and 9 fields. And the process is you evaluate, use an algorithm to determine the optimal fluence map in the beam's eye view at each of those angles, and then come up with some technique to deliver that fluence, in our case with an MLC. Volumetric modulated arc therapy, or VMAT, came along about a decade later. And the idea behind VMAT is that you can increasingly improve your ability to meet coverage objectives by introducing more IMRT fields. So what VMAT tries to do is treat from over the duration of a complete arc, and use the fact that we're entering the patient from all these different gantry angles to create a more conformal plan to the target. So some facets of VMAT are that the MLC, we will only consider one aperture per gantry angle. The MLC will move while the beam is on, and we modulate dose rate and gantry speed to adjust the dose per degree. One great thing about VMAT in terms of clinical efficiency is that it can typically be delivered with in a shorter time frame compared to IMRT. and can create highly conformal treatment plans, which is excellent. And then some reasons that we continue to not use VMAT are low dose spillage, right? When you're entering from all these different gantry points, you're creating like a massive low dose cloud within the patient. So that might compromise those volume constraints, such as the V5 in the lung. Or, you know, if there's a situation in which we want to use non-coplanar beams, that's IMRT will be superior to VMAT. So this is an image of an SBRT, a spine SBRT plan that we created with and delivered with VMAT at NYU, and it's a pretty clear demonstration of how VMAT can potentially be superior to 3D conformal therapy. You know, if we're using a computer to help us optimize MLC leaf positions at different gantry angles, then we can make these really beautiful isodose distributions where we have nice conformality to the target, and then we're able to achieve sharp dose gradients in regions like around the spinal cord or pull low dose off of the structures like the esophagus. So here's just a quick comparison. You know, what we might be able to achieve with just an APPA spine plan compared to, you know, a spine SBRT delivered with VMAT, and as I mentioned earlier, the higher dose levels conform more closely to the target in the case of VMAT, whereas with the 3D plan, they sort of spill out along the length of the patient. So what's actually happening when we deliver a VMAT plan, if you look within the treatment planning system, is that at every, the arc is specified in terms of control points. So there are positions over the duration of the arc at which the MLC leaf positions are specified and the dose per gantry angle are specified. And those are called control points. So now I want to talk about more of the specific inner workings of IMRT and VMAT and optimization algorithms themselves. But I want to make a quick note that just about inverse planning techniques, and it's, you know, it's great that we have, you know, potentially increase you know, conformality and coverage and sparing, but it comes at a cost, right? We're creating more complex treatment plans, and that can be demanding both mechanically of our machines and of our beam models. So IMRT and VMAT will require different levels of pre-treatment QA, different machine performance specifications, and then different accuracy in beam modeling, which I won't, you know, dwell on these topics, but I just want to say that we're asking more out of our treatment delivery systems, so there are more potential failure modes that we're introducing. So the overall, what's called meta heuristic for any sort of inverse planning is going to look something like this. It's not that dissimilar from what we were doing with forward planning. So initially, we still want to define our treatment objectives now in the form of a mathematical objective function. We specify we want these max doses to these structures, or at a maximum this dose to this structure, or minimum this dose to this structure, and with what priority. We're going to set some treatment parameters that are going to be fixed, such as like beam energy or collimator angle, for example, for a VMAT plan. And we'll then initialize the algorithm state. And this is something that'll be done behind the scenes. Then the algorithm basically goes through the same steps that we went through with forward planning, where it modifies the state of the treatment plan, calculates the dose, evaluates the plan, and continues to iterate until until we find that either the objectives are satisfied, the objective function is satisfied, or that we've converged and we're not making any more progress. All right, so IMRT optimization. So our goal with IMRT optimization is to produce an optimized fluence map for a single fixed gantry angle. So that's to say, if we're looking in the beam's eye view for one gantry angle, what is the optimal intensity? What does the optimal intensity map look like that will meet our coverage objectives? So as I mentioned earlier, the first step is to define an objective function with desired dosimetric constraints and weights. So a good example, people often use quadratic penalties because they're twice differentiable, and convex, which we'll get back to. But a good example would be something like this, where we can consider like we have an OIR where we want some maximum dose to be less than some value D star. And so long as that constraint is satisfied, we apply no penalty. But then if we start to violate the constraint, we add a quadratic penalty with some weight W. And that's sort of what's going on behind the scenes as far as objective functions goes. And we'll talk about more terms a little bit later on. So when the optimization is actually performed, we break down the fluence map in the beam's eye view into smaller segments, which are called beamlets or pixels. And the dose from each of those beamlets or pixels is calculated through a simplified dose calculation algorithm, and it's projected onto the patient's geometry. So all of the dose calculation for these optimization algorithms is going to be performed at the front end of the optimization process and stored in what's called a dose influence matrix. So before you start iterating or doing any of this, you do this dose calculation and evaluate for every beamlet in our beam's eye view, for every beamlet J, what is the dose Dij that's that it contributes to voxel I. And that's called a dose influence matrix, and it makes it such that when we actually perform the optimization procedure, our dose calculation is just this linear multiplication. In the case of IMRT optimization, we can use gradient-based optimization algorithms pretty comfortably because the objective function is convex. So we have our objective function, right? We have an initialized, we have some fluence map with a dose influence matrix. Now we initialize all the beamlets, say to like an open field, evaluate the, we've been careful about how we specified our objective function so we can compute this derivative of how does the objective function change depending on beamlet intensities. And then we can adjust the state of our solution either with some simplified, this is like a simple like gradient descent algorithm where we just iterate and change our solution to minimize our objective function. And fluence map optimization for a single gantry angle is wonderful because it's guaranteed to be convex, at least, yeah, it's guaranteed to be convex, meaning that the local optimum is equal to the global optimum. So the output for IMRT optimization will be these optimal fluence maps, but that doesn't mean that those are like physically deliverable. So what's required is this intermediate step of turning that fluence map into a series of MLC leaf patterns, and that's done with a leaf sequencing algorithm. So a leaf sequencing algorithm basically takes this fluence map that we decided was optimal, it satisfies our objective function, and comes up with a strategy to try and deliver that fluence given our mechanical capabilities. So there are two major leaf sequencing algorithms that I want to introduce. The first being multiple static segments or step and shoot IMRT, which is almost equivalent to delivering field in field. So it basically takes this optimized fluence map and then breaks it down into intensity levels and tries to come up with some combination of 2D apertures that can be delivered sequentially to deliver and deliver your optimized fluence map. And some parameters for something like a step and shoot IMRT would be the maximum number of segments that you're willing to use and the minimum number of monitor units per segment, and those can help control the complexity of the fluence that can actually be realized. Another important leaf sequencing algorithm is sliding window IMRT. So the approach for a sliding window leaf sequencing is that we're going to start with all the leaves. So we're trying to deliver this fluence, start with all the leaves on one side of the field and progressively move them to the other side of the field. And we leave a gap or an opening for some amount of time that's proportional to the fluence intensity that we want to deliver at that position. And I guess one thing to note is that maximum leaf speed and minimum leaf separation must be respected. So sliding window IMRT typically requires a shorter time to deliver, but requires or demands more from your machine and treatment planning system. All right, now moving on to VMAT optimization. So VMAT optimization is challenging for mainly two reasons. First, that it's a very high dimensional optimization problem, and second, that it's almost guaranteed to be non-convex. And all of the sort of challenges in creating a VMAT optimization algorithm sort of stem from these two problems, and we'll talk about them in greater detail. So starting with non-convexity. So as I sort of alluded to earlier, IMRT optimization is nice because it's basically guaranteed to be convex, meaning that if you find a local optimum, it's going to be the global optimum. This is not the case for VMAT optimization, and I guess I have a little cartoon to help demonstrate why that may be the case. So if you consider like a simple VMAT optimization where we're just trying to choose a gantry angle to deliver, say, like 100 MU to treat this target that's sandwiched between two OARs, you can imagine that if we're situated here in where the beam in what looks like the global optimum, where the beam currently is, then changing the gantry angle even a little bit might increase our objective function. But if we go all the way around nearly 180 degrees, you might find another local optimum. So the mathematical reasoning behind that is that in IMRT optimization, we're only allowing each voxel is only getting dose from a single pixel, and that's just in a simplified dose calculation algorithm. When we perform VMAT optimization, because we're considering beamlets contributing from multiple gantry angles at the same time, you can actually introduce this non-convexity. And I won't spend too much time on this, but if we consider the dose to an individual voxel as being equal to the sum of contributions from beamlet 1 and beamlet 2 with these non-negative proportionality constants A and B, and then the same situation for voxel 2, and we write out like a simple objective function where we're trying to treat voxel 2 to D2 prime and spare D1 to D1 prime, then assuming that we're violating both these constraints, we can write out all the terms in this objective function, and you'll find that you get cross terms that look like this, that imply that the second derivative of the objective function with respect to our parameters can potentially be non-negative. So that's the real complication, and why we're potentially worried about non-convexity when it comes to VMAT optimization and not IMRT optimization. So I have what is potentially a fun or potentially really silly idea to talk about this problem in optimization called the cursive dimensionality. So the curse of dimensionality is actually something that plagues us in everyday life when we're, I guess, trying to make complicated decisions. So I've thought of this real world optimization problem where we're trying to pick what would be the optimal day to spend at a beach. So if you're considering just like a one-dimensional problem, we're only considering temperature and we're averaging over all other variables, then our penalty as a function of temperature might look something like this, right? Where it's like maybe we want a warm day, but we don't want it to be blistering, and we definitely don't want it to be too cold. But if we throw in an extra variable, say having some margaritas, that could potentially introduce a local optimum or more local optima. So here's maybe where we were before on a warm day with a few margaritas, but say if it's cold out, we could still have a good day at the beach, but we just probably don't want any margaritas. And now just for fun, we're going to throw in an extra variable, maybe some food, some coconut shrimp or something. And you can imagine that this problem is becoming more complex. There's more to think about. Like, maybe if I'm having a bunch of coconut shrimp, I don't want a margarita because it's going to give me a tummy ache, and that puts me, somewhere over here. But there are potentially several local optima to have to worry about when you're trying to perform an optimization in this higher dimensional space. So in a more professionally stated, if we're given the same number of points to try and make sense of some space, it's much simpler to do with a lower dimensional space than it is to do with a higher dimensional space. That's because the size of the search space grows exponentially with dimension, right? So I mentioned earlier that VMAT optimization is a really high dimensional problem, but how high dimensional is VMAT optimization actually? So we'll just walk through like maybe an example of a problem specification where we're only going to allow one aperture per control point, as we do with VMAT. We're not trying to optimize the fluence at every gantry angle, but we're just optimizing 2D apertures at every angle and giving them a single intensity. We're going to consider 180 control points in the arc, which would be a full arc with one, for a full arc would be one control point every 2 degrees, and 120 MLC leaf positions. So if we're trying to optimize with respect to all these parameters, we're presented with this problem of sorting out 120 MLC leaf positions at 180 control points, which is equivalent to saying that we're going to have to search through this 21,000 dimensional space for an optimal solution, which sounds challenging, right? It is challenging. As an aside, since we're just talking about like the potential computational expense and difficulty of doing VMAT optimization, I just want to note that the dose influence matrix can be enormous in this situation. So dose calculation in VMAT is going to be done similarly to how it was done in IMRT optimization, where we just do all of the dose calculation up front and then store all of our results in a dose influence matrix, and then we have this linear multiplication anytime we want to evaluate dose. But that requires storing information for, depending on your beamlet resolution, which I've given an example here. A reasonable amount would be like 1,500 pixels per control point, or 270,000 potential pixels with a dose grid resolution of say like a 10 cm by 10 cm by 10 cm cube and 2.5 millimeter resolution, so a 40 by 40 by 40 grid, so 64,000 voxels. So we're potentially talking about like a roughly 35 gigabyte dose influence matrix, which in dense form, which is enormous. So my point here is that VMAT optimization, there's a reason that it came along a little bit later, and that's that there's a much higher computational demand in searching this massive space and storing a massive dose influence matrix. So here's the formal like mathematical statement of what's going on of everything that's going on in VMAT optimization. And it's not that different from what we saw with IMRT optimization. So just as before, we're going to minimize some user-defined objective function f, which is evaluated with respect to the dose in the patient D. And we're going to minimize now with respect to these aperture intensities and left and right leaf positions at every control point. We'll evaluate dose as I mentioned, is in the same way as we did before, where the dose to voxel k will just be this product of the dose influence matrix and then our beamlet intensity. But in VMAT optimization, since we're not optimizing individual fluence maps, we'll be optimizing individual leaf positions. We have to have this coordinate transformation from beamlet intensities to, I guess, some output at specific gantry angles, and then left and right leaf positions. And all this expression says is turn on Bixel ij phi if with value y phi if the Bixel falls between the left leaf and the right leaf. And then it's a constrained optimization problem. We're not allowing ourselves to take MUs out of the patient, so we want non-negative MUs and we want non-abutting MLC leaders. So what that looks like in terms of how the output of our optimization problem is going to be specified in terms of left and right leaf positions and aperture intensities for up to 180 or more control points. So here's just an example of what that might look like. So here's just 180 control points with different colors showing what intensity you might deliver through that aperture, and then the left and right leaf positions. So we're not optimizing individual fluences, but just direct machine parameters. So different treatment planning systems will have different approaches to VMAT optimization, but there's sort of like two main ways I guess two main ways that it's been implemented commercially. And we'll just talk about each of them pretty briefly. The first, and they're both a mouthful, so I don't know. It's not really important to know the terminology, but we'll go through it. The first is direct aperture optimization, which is, as I said, we're optimizing with respect to individual leaf positions. Global direct aperture optimization with geometry-based segment initialization, and that's implemented in some form by Varian's RapidArc. And then the second is local direct aperture optimization with fluence map optimization informed segment initialization. And we'll talk about what all of that means, but that's employed by Philips' SmartArc, Oncentra VMAT, RaySearch RayArc, and Electa Monaco. And it's going to be the same in principle as we discussed in IMRT optimization, where we have some representation of our MLC leaf positions. We evaluate dose. We use that dose to evaluate our objective function, and then feed that back into how we're correcting our leaf positions. So the first algorithm that I want to talk about is the global DAO with geometry-based segment initialization. And the sort of the vision of this algorithm is to reduce the dimensionality of the optimization space as much as possible. So at the initialization of a global DAO search, we at least in Eclipse, they only consider beamlets and leaf positions that will contribute to the target dose or to the dose within 6 millimeters of the target. So right off the bat, we're throwing away all of the beamlets, all of the leaf positions that all of the beamlets and all of the leaf positions that aren't anywhere near what we've defined as a target. The second thing that we do is if the user has defined any sort of avoidance sector or avoidance structures, to cut those out as well. So as we've been talking about, the full VMAT problem specification is a very high dimensional problem, but the key insight to being able to do global direct aperture optimization is that when we initially approach the problem, we don't need to do it in the full super high dimensional resolution. We can use lower dimensional solutions to initialize a higher dimensional search. And that's done, at least in variance case, with what they call progressive resolution optimization. So the idea is that we start off not by searching through 180 control points and with very fine MLC precision, but to start off with a more manageable, like 15 control points, and progressively increase the resolution while using the old solution to initialize the higher dimensional search, if that makes sense. And schematically, just thinking about what's going on here, if you imagine some terrain, which would be our objective function, and we're trying to find the highest point in this terrain, the approach with the progressive resolution optimization is to maybe take, if we were to break this up and to find the average elevation for each of these quadrants, and then just navigate to whatever quadrant that is, and then find the average, and then perform the same thing in 16ths and in 64ths. So during each of these resolution levels, the state of the optimizer is improved, but we can't use the same algorithms that we were using in IMRT optimization, the gradient-based methods, because of all of these local minima. So we have to use what are called stochastic optimizers. So there are lots of different implementations of stochastic optimization engines. Like genetic, you can use genetic algorithms, but the one that I'm most familiar with, and I know that has been implemented in several VMAT algorithms, is simulated annealing. So the idea behind simulated annealing is that you have your solution state, and you randomly make some change to that state. And if it improves the score with respect to the objective function, then you accept that change. If it worsens the score with respect to the objective function, then you accept that change with some probability. And that probability varies over time according to some annealing schedule. And it's like a cooling process. So the idea is that you're able to search this high dimensional space without getting trapped in local optima, because you've incorporated some sort of randomness in your search procedure. So back to this slide, that's the basic summary of what's going on with the global DAO algorithm. The objective is to reduce the dimension of the search as much as possible, and then use a stochastic optimizer to navigate those increasing resolution search spaces. Now I just want to talk really quickly about the local DAO algorithm with fluence map optimization and informed segment initialization, which is used by all of these vendors. So the idea behind, I guess the key to this algorithm is this fluence map optimization and informed segment initialization. So the idea here is that if we perform fluence map optimization as we did in IMRT optimization, where it's convex for each of these gantry angles individually, and then come up with some way to approach that solution with an arc through some arc sequencing algorithm, then that's going to give us a pretty good solution. And we can apply some final corrections with a gradient-based algorithm. So what's actually done with these algorithms, and there's several different implementations, but the idea is that you perform You perform convex fluence map optimization at several gantry angles. You perform some interpolation between those angles, perform arc sequencing, which just takes these fluence maps and turns them into left and right leaf positions and aperture intensities, as we discussed before, and then use that to initialize your search of the full VMAT search space. And that can be done with a gradient-based optimization algorithm. So the idea behind the local DAO algorithm is that we want to choose a very clever initialization and then use a gradient-based optimizer. So if we had to compare the two, just in a two-dimensional optimization, something like this, here I have the global DAO algorithm shown in red and the local DAO algorithm shown in blue. So we might expect that the local, they might arrive at the same solution, but the local DAO algorithm might start off with a better looking solution and then use gradient descent or some other gradient-based algorithm to descend to a nearby local optimum. And a geometry-informed global DAO maybe has a worse initialization, but can sort of mosey its way over to a satisfactory solution. So now I just really quickly want to go through some other planning adjacent algorithms and important optimization objectives that you might use clinically. So an important one, especially for IMRT optimization, will be this smoothing objective. So many treatment planning systems will incorporate smoothing objectives either implicitly or explicitly. And the idea behind a smoothing objective is that it controls the gradients within that optimized fluence map so that you maintain fidelity during this arc sequencing procedure. If you come up with, you perform fluence map optimization in some crazy high resolution and produce a fluence map that has that's insanely modulated, it might look, really beautiful on paper at this point, but when you try and physically realize that with the machine through some arc sequencing algorithm, you'll find that it's not possible or it's significantly degraded. So the idea behind the smoothing objectives is so that you don't lose fidelity during this step. MU objectives are kind of similar in that they, I guess, help to control the complexity. So the number of monitor units per prescription dose is usually a good measure of plan complexity. And constraining the number or the maximum number of MUs that you're going to allow for an ARC, for example, might make your plan more feasible. So if you were, for example, creating a bunch of treatment plans that are insanely modulated and they look great in the treatment planning system, and then you go to do QA and you find that they're failing every time, you might consider adding a maximum MU objective to limit the complexity of the treatment plans so that you can actually deliver them. Another useful optimization objective, which is implemented in, I know, Eclipse for sure, is this normal tissue objective optimization, or normal tissue objective. So it's just an alternative to the conventional shell or ring structures, which help to improve conformality to the target. So the idea behind the normal tissue objective is that you specify some dose fall off that you're looking for, and and voxels are penalized depending on their distance from the PTV, and whether they're meeting the fall off that you specified. And this is a great thing for SBRT, for example, where you want very tight isodose lines, but maybe not so great if you're trying to carve dose out of specific structures, because it penalizes all voxels uniformly, just depending on their distance from the PTV. Another really and useful objective is an automatic feathering objective. So one problem with using multiple isocenters. If you're going to treat a patient using multiple isocenters, is that depending on how the patient is set up, there might be hot or cold spots at the junction, right? But if you're using IMRT or VMAT, then you can use an automatic feathering objective, which, say if you have a target and you're trying to push dose to that target, you can the optimizer will specify which will vary the weights on each voxel so that you get an equal contribution to the dose in the overlap region from each field, and that's useful because it increases robustness, and you don't have to worry about necessarily like hot or cold spots at the junction. So I don't have a bunch of time left, but I'm just going to breeze through these topics in treatment planning research. I'm not an expert on all of them, but I think that they're all just good to be aware of. The first is biological optimization. So when we create radiation treatment plans, right, we're using radiation dose as a proxy for biological response. What we're really after is, can we effectively treat this tumor and not cause any complications, right? These are the relevant values: the tumor control probability and normal tissue complication probability. And in principle, there's nothing stopping us from using these values in our optimization objectives that we just went through, or using something adjacent, like something that might be of more biological significance, such as the equivalent uniform dose. So these biological optimization options I know are available in some commercial treatment planning systems, but it's my understanding that they have limited applicability just due to uncertainty in biological models. So I guess the idea is that you can use them, but you should at least verify that the nominal dose distribution or the physical dose distribution looks clinically reasonable if you're going to optimize based on biological parameters. Another interesting topic is knowledge-based planning. So the idea behind knowledge-based planning, which again has been commercially implemented, is to take the information from previous patients that you've treated and automatically populate optimization objectives. So, given this patient's treatment geometry and anatomy, what do we think are the feasible objectives or optimization objectives for this patient, and then to auto-populate and auto-populate those parameters. And that's potentially a great time saver and very exciting. And then another topic is multi-criteria optimization. So it's no surprise to anyone that in radiotherapy, we often have competing optimization objectives. So for example, like prostate, if you're treating a prostate, like prostate coverage versus, bladder dose. So that might be there might come a point if you have a really excellent plan where you can't increase your prostate coverage without further increasing your bladder dose, and that point is called the Pareto front. So we have two competing optimization objectives, and there's a point at which you can't really improve one objective without worsening another objective. So just so that everybody's comfortable with the terminology, planning solutions where one objective can't be improved without worsening another one are called Pareto optimal, and the set of Pareto optimal plans is called the Pareto front. And the Pareto front is difficult and takes a long time to sample in radiation therapy because it requires multiple optimization runs. I know that some treatment planning systems currently support multi-criteria optimization, or like this sampling of the Pareto front, and allow you to explore trade-offs. And I know that it's like an active field for current research. People are using like deep learning to try and predict the Pareto front for given plans. But I guess the current MCO algorithms, the idea is that you start with an already good plan that you're pretty happy with, specify which objectives you're willing to perturb and within which range, and then you rerun several simplified optimizations starting from that initial plan, and then hopefully get some idea of what trade-offs are available. All right, the last topic that I want to talk about, and the one that I'm personally most excited about, is robust optimization. So robust radiation treatment plans should be robust to geometric errors. This is no secret. And it's conventionally we handle geometric errors with the use of margins, right? So this is just this figure that hopefully everyone's familiar with from ICRU 62, demonstrating all the different margins that we use in radiotherapy and why. So in principle, setup margin should work under the assumption that it's called the static dose cloud assumption, where you assume that the dose distribution is unchanged by the shifted or modified patient anatomy. So in a perfect world, we plan with a PTV and the patient set up properly. The CTV sits happily within the PTV. Our prescription isodose line surrounds it, and all is well. The purpose of the PTV is for these situations where maybe the patient is set up slightly improperly, and it's under these conditions that we're assuming that this isodose distribution hasn't changed, and that despite the patient being mispositioned, they can still be treated to prescription. So this is a pretty fair assumption for most photon planning, but it's not really fair all the time, depending on beam arrangement and inhomogeneities. So like a plan that consists of only coplanar beams might be more sensitive to shifts in one direction than another. So I don't know, that might be a possible complication, or anatomical motion can be difficult to predict. But all of these uncertainties are, the objective of robust optimization is to address these uncertainties by modeling them within the optimization software. So the idea is that we have, rather than optimizing with respect to just one objective function that we specify at the beginning, we specify our objective function, and we evaluate nominally, if the patient is set up perfectly, this is how we score. The robust optimizers consider at every iteration if the patient is set up 3 millimeters to the right or 3 millimeters to the left, or if our CT calibration curve is in error by 3%, what are the consequences for our patient dosimetrically? And so what our robust optimizers try to do is at every iteration, rather than just optimizing with respect to a single objective function, to push this this distribution of objective functions, or the maximum potentially maximum score objective function, to closer to 0. And I think this is a really exciting idea, and has some potentially interesting implications for the nominal dose distributions. And I'll leave everybody to do their own research, but I'm very excited about it. So robust optimization is already clinically implemented for setup and range errors all over the place for proton therapy. And I guess that's where it's needed the most, because of the sharp fall off of the Bragg peak. But there's a figure here from this paper, which I highly recommend, Robust Radiotherapy Planning. It's just a survey paper comparing robustly optimized intensity modulated proton plans with conventional proton plans, which are which are based on margins. And you can see that, and this is modeling CT calibration curve errors. And the plans that aren't robustly optimized potentially have greater changes or greater dosimetric effects. There are other potentially interesting uses for robust optimization beyond just like geometric errors. One of which being using, for example, a 4D CT to represent the probability of anatomy to being in different positions. And there have been some interesting studies comparing plans that try to minimize the expected value of the objective function versus like margin-based plans. And the nominal dose distributions again look sort of silly, but when you look at the expected value of the dose distributions under their error models, you'll find that more often than not, we're sparing structures that we want to spare and treating the structures we want to treat. So I think that this is clinically implemented in Ray Station, but I have not had any practice with it. So I just want to take a minute to thank. I've spent a good amount of time talking to these two at NYU about putting this, about all these algorithms, and they helped me put together the slides. So otherwise, I have no more to share.